So yeah, I wanted to update you on what's been happening with seL4 verification recently. We've got lots of projects that we're working on, so I wanted to let you know about the status of all of those and a little bit about our plans for the future as well. So this talk is going to have a bit of an overlap with a talk that my colleague Raf gave a couple years ago when he spoke about all of this, but I'll provide you some updates and I'll also give a bit of a different emphasis on things as well. But before we get to the details, I should give you some background information on seL4 verification. So seL4 is the world's most highly assured operating system kernel. We have unparalleled mathematical formal proofs of correctness and security. So I'll tell you more about correctness and security, what I mean by those, in just a second. But the upshot is that seL4 is the most trustworthy foundation out there for safety and security critical systems. Okay, so let's take a closer look at what we mean by correctness and security. So I'll use these handy diagrams to help me tell you all about it. So on the left here, we have one of these radar-style diagrams that I'll use throughout the talk. So we've got seL4 at the center, and then in different layers building on top, we've got our different kinds of proofs that we have about seL4. So they get more abstract as they go up. They're about high-level properties, and they kind of build on each other as well. So the first layer here, down the very bottom, is binary verification. This is a collection of proofs that we have about the binary of seL4. And at the very top, we've got the system initialization proofs. As interesting as these are, I won't be talking at all about them today. I want to focus on the inner two layers that we've got here. So the larger of the two layers is functional correctness. And there's a lot to say about that. So if we just zoom in a little bit, we can see that we've got three layers here. So these are different specifications of seL4 that we work with, and they get, again, more abstract as we go up. So the bottom layer is formalized C. We take the C code from the kernel, and we pass it through a translator, and we end up with a formalized C, which we can work with in our theorem prover. It's a very faithful translation of the C, so it's got lots of horrible, gory details, exactly the same data structures that the C has, and yeah, very low level of abstraction there. So we step one level up and we get to the design specification. So we actually maintain a completely separate version of seL4 written in Haskell. And then we again automatically translate that and we get to the design spec. So that serves as like an intermediate layer in our framework here. And then the most abstract specification that we have of seL4, we just refer to as the abstract specification. So we write this ourselves, we write it directly in our theorem prover, and this is really our expression of the true intent of seL4. It's exactly what we want seL4 to be, it does exactly what we want seL4 to do, and it's written in a nice way for us to more easily reason about the kernel and all of its nice properties. So now we're in a position to say exactly what we mean by functional correctness, and by that we mean that the formalized C is a correct implementation of our abstract specification. Or we could say slightly more formally that the formalized C is a refinement of the abstract specification. Okay, so in order to prove functional correctness, we need a very large number of invariants that we've got off to the side here. So these are nice properties about the kernel state that are preserved by the abstract specification. And that also increases our confidence that the abstract spec is exactly as we would like it to be. Okay, so what does that actually mean? So functional correctness is the strongest form of correctness that we can show for any piece of software. It's much stronger than what you would get if you were, say, doing static analysis on the kernel or something like that. Way stronger than if you were to just get an expert to check through all the lines of code that we have in the kernel. So it's a super strong guarantee. And then the next layer up, building on top of functional correctness, we have the security proofs. So the security proofs have the two properties, standard security properties, of integrity and confidentiality. Integrity says that a user running on top of seL4 would only be able to write to a memory location if it's explicitly authorized to do so. So we've got data integrity, and then confidentiality says that that user could only read from a memory location if it has authorization to do so. So that makes up the security proofs. If that was a little bit too much detail for you, then you can think of correctness and security in a very rough way. So correctness says that the kernel's not going to crash. And then security says that you can create certain types of isolated systems. You could have a system with a couple components. You could pull all of your trusted applications into one component, all the untrusted things into the other, and you'd have perfect isolation between the two. So that's the sort of thing that we prove about seL4. And as cool as that all sounds, and we've got all those proofs for at least some versions of seL4 running on some architectures and platforms, we're always interested in ways that we can advance seL4 itself and the verification story that we have for seL4. So we've got lots of ideas in mind of exactly how we'd like to go about doing that. So we'd like more architectures verified, more features of seL4 verified on more platforms, and we want seL4 running on more cores verified. And sometimes less is more. We would also like less of a need for expertise in developing all of these proofs, and less of a need to maintain this ginormous number of proofs that we now have about seL4. So we are working on a project in each of these areas. I'll go through all of them. I'll mainly focus on the first two of these points during the rest of my talk. But let's have a look at the last three here, just quickly. So we want more platforms verified, and for this we're working on automated platform port verification. My colleague Gerwin spoke about this at last year's seL4 Summit, and we also heard Darren refer to this very nicely. So I won't say much more about that, but I'll give you an update on where we are with it. So if you go onto the seL4 website, you'll find a long list of 32 platforms on which seL4 is currently running. So we've got verification working for 18 of them at the moment, and we're looking to get between 90 and 100% of those platforms verified in this way. And then any new platform that comes along that you would like verification for, we're wanting to just provide automatic verification as long as the platform satisfies some mild constraints. So that's very exciting. We're working on this with funding from DARPA at the moment. And this is also great because, yeah, as Darren said, this is much less of a need for expertise in these platform ports. Okay, so on our next point, we wanted less of a need for maintenance of all these proofs that we've got. And for that, we're working on the proof architecture split. So again, Gerwin spoke about this last year, and Darren also mentioned it. But this would be fantastic because it would greatly reduce the duplication that we have in all of our proofs. So much less of a need for maintenance of all of the proofs that we've got, and also probably makes a lot of the projects that we're working on just much more quick, much more agile to develop. So again, DARPA is funding us to work on this project, and the status of that. So we have the abstract invariants, all these nice properties. We've done the Arch proof architecture split for that. And at the moment, we're working on the rest of the functional correctness proofs. Okay, so our last point here, we wanted seL4 running while verified on more cores. So the next talk after mine is Corey's talk, my colleague Corey, and he'll tell you all about that. Okay, so let's come back to these first 2 points. We wanted seL4 verified on more architectures, and for this we are working on ARM's 64-bit architecture, which we call ARCH64. So let's take a look at this. This is one of our radar diagrams from before, but now we've got all the architectures for which we provide verification. So we've got on the right-hand side the RISC-V 64-bit architecture. Down the bottom is Intel's x86 64-bit architecture. On the left, we have ARM's 32-bit architecture, and we've got versions with and without hypervisor support. And then all the new stuff's happening at the top. So that's ARCH64 with hypervisor support. So recently, we've finished the functional correctness part of the ARCH64 proofs. That was with funding from NCSC. So as far as correctness goes, we have full correctness guarantees for ARCH64 on par with all of the other architectures that we support. So at the moment, we are working on the integrity proofs. That's the first half of the security proofs. And we're expecting that to be done sometime in the next quarter, or in first quarter of 2025. Okay, so our last point here, which I'll focus on in the rest of the talk, is that we wanted more features verified for seL4. And for that, we're working on the MCS version of seL4. I've been working on this for now many years, so I thought it would be a good opportunity to tell you what's been happening with that. And also tell you what MCS is, if you haven't used it already. So MCS is a version of the seL4 kernel that provides support for mixed criticality systems. So what on earth is a mixed criticality system? So I'll give you an example in a second, but at a very high level, a mixed criticality system has lots of different applications running on it, all executing on the same hardware. And we've got some applications at a high level of criticality and some at a low level of criticality. So they mix the levels of criticality in the system. That's how it gets its name. So what do we mean by a high level of criticality? So that would be if failure of that application would lead to something catastrophic. So it could be death, environmental ruin, something really bad like that. And then at a low level of criticality, we've got things where failure would just lead to a downgrade in the user experience. So nothing really bad happens, it is just not great. So my favorite example of a mixed criticality system is a self-driving car. So here's my somewhat simplified model of a self-driving car. It has just two applications. So one application controls the steering, and then we've got a speaker system so we can listen to music while we ride around in our car. So I hope you would agree that the steering system is at a high level of criticality, and then we've got our speaker system at the low level of criticality. So in designing systems like this, if we're not very careful, if we don't design our system well, then we can run into the horrible situation where an application at a low level of criticality just completely monopolizes CPU time. So that's horrible because it won't allow anything at a high level of criticality to ever run on the CPU. So hopefully you can see in our example of a self-driving car why that would be terrible. We would be happily listening to the Red Hot Chili Peppers as the car is going at 100 kilometers an hour down the road with no opportunity to steer. So that's a terrible situation, and we would like to avoid that. And the way that we do it is by using MCS. MCS provides us ways of designing systems where this kind of thing never happens. So how on earth does it do that? So the idea is that it uses time as a resource. So we're probably used to thinking of system memory as a resource. We would be very interested in who has access to the memory, at what times, what kind of access, all this sort of thing. And the idea in MCS is that we would do a similar sort of thing for time. So we would be very interested in who has the rights or the capabilities to use time on the CPU. So MCS achieves this by introducing a new kernel object. These are scheduling context objects. I'll tell you a little bit more about those a little bit later in the talk. It's a very interesting way of dealing with this problem. So the proofs have evolved over the years. Most of the changes that we have to seL4 are very small, maybe just a few lines, something like that. Some of the changes don't have any impact on verification at all, so that makes my job easy. I don't need to do anything. And they just normally merge those changes into the kernel very quickly. Some of the changes that we get to the kernel have a fairly small impact on verification, so maybe after a few weeks or something like that, we finalize the proofs, and once the proofs have been finalized, then we'd be able to merge those changes into seL4, make sure that it's always up to date with verification. But occasionally we come across some larger features of seL4 that take us a little bit more time. So a couple examples of this would be some features we've introduced over the years. One of them was bound notification endpoints. I think this took someone maybe on the order of like a year or two to verify. Bitfield scheduler optimization was another project that we did a while ago. That took maybe about 6 months or so, but without too much pain, we were able to get the proofs all sorted, and then we could merge these new features into MCS, into the kernel. Okay, MCS is quite different though. MCS is a very large change, and it's a very invasive change as well. So such a large change that we decided to fork the development of our proofs. So we now maintain two lots of proofs. We've got one for the non-MCS version of seL4. So we continue to provide all of the guarantees and assurance that we normally do. And then separately, we're developing the proofs for MCS. So here's how we're working in parallel with these two developments of proofs. We have the non-MCS version of seL4 with all of the proofs that I mentioned just before for all these different architectures. And then for MCS itself, we are working just on a couple architectures at the moment. We've got ARM's 32-bit architecture and then RISC-V 64-bit. So over the years, we've been funded by many different organizations and institutions. We have completed a very nice collection of invariants about the abstract state. We've done the top half of the refinement proof, so this says that the design spec correctly implements the abstract spec. And at the moment, we're working on the lower level of the refinement proofs. This is funded by DARPA, and we're currently showing that the formalized C correctly implements the design spec. So that's what we're doing at the moment, and it's taken quite a while. We've had some challenges along the way, and I thought it would be interesting to go through some of these difficulties, see what MCS has to offer a proof engineer. So what makes it so difficult? There are a few interesting reasons. So we've simply got many new lines of code in MCS. So I think the kernel, just the non-MCS version of the kernel is around 10,000 lines of code, something like that. MCS is about a 15% increase on that. So it might not sound like it's a big jump, but due to the nature of seL4, it's just such a highly interconnected system. So you make a few changes to the kernel, and suddenly they ripple throughout the entire kernel and throughout all of the proofs as well. So we have seen that all throughout seL4 verification, and it's certainly the case that this happens to MCS as well. So we've got some new kernel objects, the scheduling context objects I mentioned before. We've got reply objects as well. We've got lots of new invariants that are required. So invariants tell us nice properties about the system. There's an awful lot more going on in MCS, so we need to know much more about what's happening in the kernel. And so we've got lots of new invariants that we've come up with. And lots of the invariants from the non-MCS version of verification have been impacted as well. So all this new functionality needs to be carried out by many new functions in the kernel. So I think it was like 500 or so functions in the original kernel. Now we have many more. And in particular, we've got new system calls that the users can make. And many pre-existing functions are now much longer. So that makes verification more difficult. Longer functions mean that it can be more difficult to show that the functions preserve the nice properties of the system. And in all the three different specifications we have to make sure that all these functions line up nicely, carrying out the same kind of thing. So that makes our job a little bit tougher there as well. So loops is the last thing I'd like to talk a little bit about. So we had loops in the non-MCS version of the kernel, but now we have many more loops. They play a much more prominent role. Loops are always a bit of a difficulty for verification, and that's definitely the case here. But I think they're super interesting. It's been really fun in a way to verify some of the loops that we've got here. And I thought it would be interesting to go through one example, just a bit of a technical deep dive to give us a bit of an idea about how MCS works and some of the challenges that we've come up against in the verification. So we'll get a little bit technical here, but hopefully you'll find it informative. Okay, so let me set the scene here. Let's just say that I'm the current thread, and I've been running on the CPU, and now I don't want to run anymore. I'm all done. So because I've been running on the CPU, and I'm running on the MCS version of the kernel, I had to be associated with a scheduling context. So this has got all kinds of information about scheduling. So one of the most important features of the scheduling context is a so-called list of refills. So here are my refills. I've got 4 of them. Each refill starts at a particular time and goes for a certain length of time. And this is supposed to represent the actual time on the system during which we are allowed to run with this particular scheduling context. So time goes to the right, of course. I wouldn't be able to run at any time before time t0. But at time t0, it could run on the system for a little while. It can run for a certain length, given by the length of this first refill. Then after that, I wouldn't be able to run for a little bit of time, but if I waited around until time t1, then I could again run for a little bit more time. So this is how we manage the time on the kernel, and we need to do all kinds of calculations with this to make sure that everything works nicely. So let's just say that I use time equal to this blue box here. And if I've used time, I need to be charged for the time that I have used. So, I mean, just ignoring a few details here, it gets very heavy with details very quickly. But maybe one thing that we could do to charge this scheduling context for the time it's used is to just chop it up like this. So that seems good to begin with, but there is a bit of a problem here. So the problem is that this first refill is now maybe just a very short amount of time. Might not even be enough time for us to get back to get out of the kernel and then back into user space for us to actually do stuff. So the problem in MCS is that all time used by the system needs to be accounted for by some scheduling context, including all the time that we spend in the kernel. So we need to be prepared to get out of the kernel and then get back into the kernel for any time that we start running a new thread. So the MCS model of timing relies on there being a worst-case execution time for the kernel. So the problem is that we would like to have at least 2 times the worst-case execution time of the kernel in the first refill in our list here. So how can we make sure that we do have that? So by the way, one worst case execution time to get out and then one back to get back in again. So I've got a solution in mind, and here's how it works. I'm just going to merge some refills together. So in our model, we're able to take a refill and we can push it forward in time. We can't take it back in time, but we can push it forward. So let's try that. So we're just going to push it until they merge together like that. And we're just going to keep doing this until we end up with 2 times the worst case execution time in the first refill in our list. So this sounds like a loop, and this is exactly how it's written in the kernel. It's just a while loop, and it says as long as the time isn't enough, just keep merging. And keep merging until we have at least 2 times the W set. Okay, so loops are scary, right? Every time we introduce a loop, we need to be worried about termination of the loop. And so we need to think about when this loop of ours is going to terminate. And the scheduling context must have a budget. So budget is just the total amount of time that the scheduling context could use. We need to make sure that that's at least 2 times the worst case execution time of the kernel. And this means that we would like this to be true of all of the scheduling contexts in the entire kernel at all times. And so this is a new invariant that we would like of our state. So introducing invariants like this can sometimes be a rather daunting task. The invariants generally need to be shown to be preserved by all of the functions in the kernel. And this is what we have done with this invariant. Because we're only touching a very specific part of the scheduling context object, it's actually not too difficult to show that this is preserved by most of the functions in the kernel, but it is a real pain to show that this is preserved when we actually start charging time and manipulating time in the system. Okay, so that's most of what's going on in this loop, but there's lots of other stuff that has been a little bit difficult for verification. So all of the time, the amount that these refills can run for, they're represented as words in the system, so we're adding words together, which is no fun for a verification engineer. We have to worry about overflow and all that kind of thing. So that was really difficult to deal with. One other thing I could mention here is data refinement. So we've got this version, we've got this loop in all 3 different versions of our specification, and they operate in slightly different ways. The C and the design specification have this as a in-place ring buffer, but then the abstract specification has a nice list for us to play with, so we can much more easily show some nice properties about the list of refills that we have. So that's the end of the technical part of the talk. Hopefully it wasn't too bad. Hopefully you've learned a little bit more about how MCS works and a bit of a day in the life of or day in the 3 months of a proof engineer working on verifying something like this. Okay, so just to wrap up, we've been busy at work on lots of different areas, verifying lots of cool things, and making sure that seL4 is the best way to build a verified feature. Thanks.
Nice talk. This is Zikai from ETH. So I have a question. When you verify for architecture like ARM64, do you account for like the ARM trusted firmware, or how do you handle those firmware running at a higher exception levels? Thanks.
I might ask Gerwin to answer that one for me.
So the answer is right now in the configuration of the kernel that is verified, you're not allowed to call into trusted firmware. So basically, we assume it has set up, a reasonable initial state and is dormant afterwards. We are about to look into what we need to do for SMC calls, which would be calling into a basically unverified piece of software that has higher privilege than seL4. The assurance story there basically is, well, if you haven't verified that and you're just calling it, that's your problem. you should verify it. In the seL4 design, there is a configuration where you're allowed to do it, and it allows you to restrict what calls you can make. So, for instance, you could say, okay, I really need this for this driver to modify the power state of the machine, for instance. And if you want to build a high assurance system, you could then concentrate on, okay, I'll look at the implementation of this one syscall. I don't care about the others. This one you're allowed to make in the high assurance setting. And seL4 will make sure you only make that one. And what we will be verifying is the mechanism that makes sure you will only call this one. The onus on verifying that the actual call is fine is still on, that system and what trusted firmware you're running and so on and so forth. Because, I mean, it's different for each board and each manufacturer and so on. So, yeah. So that's the story for that.
Just curious about the proofs you have marked as future. Is that, are those things that you have funding for, or they're just high priority on your roadmap?
So maybe I will ask June to answer that one for me.
It depends on which one. So talk to us, but yeah, some we have funding for, and some of them, like, yes, it really depends on which ones. So they are all things that are on the roadmap because we want to do it and because the community needs it. And some we have funding for, some we are looking for funding, and some are just plans.
I think this will be the last question.
Hello. You forked the proof between non-MCS and MCS.
Yep.
Is the plan to bring those together or to ditch the non-MCS one when the MCS one becomes available?
Yeah, so once MCS proofs have been finished on all the different architectures to the point that we would like to, then MCS will become the default configuration of seL4. I think that's the current plan. So yeah, once that happens, then it'll just be MCS. We'll be back to the one version of all of the proofs, which makes my life a lot easier, and yeah, that'll happen.
Actually, we might have time for one more, if there is.
Suppose you're done with your MCS proofs. Can I then do provably correct hard real time?
That is an interesting question. I think that has been discussed at some points. I don't know of any current plans. Maybe Gernot has something in mind there.
It's on our roadmap, and we do have funding for it, but I'm not making any promises at the moment how far it will go in. But we are about to start working on it.